Okay. Let's look at this problem that you voted off the island. It's an old exam problem. I find that people have more trouble with the rotational motion problem on this exam than any other problem. People are missing the idea of this inward seeking acceleration and hence the inward net force. And so what I would encourage you to do, what I would beg you to do, is when you get that exam Thursday night, just go looking for the problem with the circular motion. There's got to be some problem in there where something's going in a circle. And as soon as you find it, take a different colored pen and just remind yourself that the acceleration has to be towards the center of the circle. Because what you're doing is you're seeing, oh, it's got a constant velocity, so it's got to have a free body diagram that's balanced. No, it's got a constant speed of 2 meters per second, but not a constant velocity because it's going in a circle. It has a centripetal acceleration, and that centripetal acceleration is given by v squared over r. That's what we got from Galileo. Now that'll be on the front page of the exam, that formula there. In this problem here, we have a speed of 2 meters per second and a radius of 0.5 meters. Now folks, I wish it weren't so, but I'm here to tell you that one of the most common mistakes is to not square that. Oh, some of you will put the square in your formula, then you won't do it in your calculator. Look to the person on your right. Let's let it be them. Okay? Don't let it be you. Okay? So this is going to be 4 over a half, or 8 meters per second to the left. Okay? Now, in B, we need a free body diagram. And I find as I'm working with students in my office that many of you are not following the recipe. I've been very careful about following the recipe to the point where you're getting tired of hearing me say certain things. Like, the first thing I put on any free body diagram is, finish the sentence, weight force. And in this case, it's a 0.6 kilogram cup, and I multiply that by the gravitational field strength of 9.8, call it 10 newtons for each kilogram, and I get 6 newtons. I then ask, what do I ask? Are there any magnets in this problem? In this case, no. After that, all forces have to be contact forces. So I ask, what touches the cup? The Lazy Susan. So I ask, does the Lazy Susan push or does it pull? If it's not a chain, if it's not a rope, if it's not a string, if it's not a thread, if it's not one of those 4 things, it's not pulling. We'll talk about pulling. This lecture is all about pulling. But the Lazy Susan's not pulling, it's pushing. And whenever one thing pushes on another, there will always be a normal force, Lazy Susan on the cup. And by normal, I mean perpendicular. Perpendicular to this surface between the Lazy Susan and the cup. If the Lazy Susan is beneath the cup, then a push has to be up if it's perpendicular. Okay? That's how you know how to draw the normal force. Now, finish the thought. Whenever one thing pushes on another, there will always be a normal force. There may also be a friction force. Now the friction force has to point parallel to the surface. That means it has to either point left, right, or it can be 0. Now do I want this diagram to scream left, right, or 0? Left. I want it to scream that acceleration, and that's why I went looking for this problem on the exam and drew that arrow there. So that means I've only got one force left in my quiver. It's got to point this way. It's a static friction because there's no slippage between the cup and the Lazy Susan. Lazy Susan on the cup. Now, when I find that static friction force, I don't use a static friction force equation because there is no static friction force equation. There is a formula for when we break free of static friction, what the maximum static friction can be. But when we're looking for the actual static friction, we use Newton's second law, F net equals ma. And I always get to use Newton's second law twice. Once in the y direction, once in the x direction. In the y direction, there's no acceleration. And so that means that this normal force has to be 6 newtons. In the x direction, my only force is that static friction force, Lazy Susan on the cup. That's got to equal the mass of 0.6 kilograms times the acceleration of 8 meters per second squared left with a t, and that gives me 4.8 newtons left. And that's the answer. I really wish it were harder. If it were harder, I'd feel better about all the money they were paying me. You know, I wouldn't feel so guilty. But it is what it is.
Instead of saying go back, you say toward the center.
Towards the center would be even better. I'd give 27 extra points for that. Yeah. 27 and a half. Okay. Are we good? Is that problem okay? Okay. Does this bring back the pain? Yes. In this tutorial, you were told that the hand pushes with a constant push and that the table was frictionless. Now you know that if I have a frictionless table, things go at a constant speed in a straight line if I don't push them. That block of dry ice just keeps on going. If I push on something, it speeds up and it would accelerate to the right. Okay? And everything's accelerating together because they're moving as a unit. Now, you were asked to draw free body diagrams for block A, block B, and this heavy rope that's connecting them. Now, the diagrams I'm going to draw right now are not correct, but they are the diagrams that many of you drew initially. Okay, so recognize that these are not correct. You said, well, the earth pulls down on A and the table pushes up, and the rope pulls to the right. The earth pulls down on B and the table pushes up on B, and the rope pulls to the left. And the hand is pushing on B. And then you said, well, if the rope is pulling to the right on A must be pulling to the left on B, on A, I'm sorry. And if the rope is pulling to the left on B, B must be pulling to the right on the rope. And then you said, oh, it's a heavy rope. And at that point, many of you stopped. Now, if your instructor was doing his or her job, they came up to you and they said, hey, what gives? You just told me a moment ago that everything had an acceleration to the right. Well, that screams to the right, and that screams to the right. That doesn't scream to the right. And so you fixed it. Watch. Watch carefully. Pow! That screams to the right. And then your instructor said, yes, 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 it does scream to the right. But there's also this other scream, down. How do you account for that? And many of you, not all of you, but many of you said, oh yeah, we need a force up. And then if your instructor was doing his or her job, they challenged you to find a boogeyman for that force. What thing that you can taste, smell, touch causes that force? And when you can't find a boogeyman for a force, that force does not exist. And then I hope you recognize that where the rope is attached to A and where it's attached to B, it sags. It's a heavy rope. And a rope can only pull along the length of that rope. And so that means that the force by A on the rope is going to be up and to the left. It's pulling up and to the left on that rope. Where B is pulling on the rope, it's up and to the right. Up and to the right. And these two forces here are how you get rid of that downward stream. Okay? Now, that has some consequences. If this force by A on the rope is up and to the left, by third law, the force on A by the rope is down and to the right. Okay? Equal in magnitude, but opposite in direction. Now, if this weight, I'm making this up, if this weight is 60 newtons, is this normal by the table 60 newtons? Yes or no? No, because there's no acceleration up or down. This force has to balance this force and this force. Both of these. Okay? And so that normal up has to be bigger than the weight. Now, likewise, if B is pulling the rope up and to the right, then the rope is pulling B down and to the left. These are third law companions here. And again, because of this downward component here, and the fact that there's no acceleration up or down, this normal force has to balance both this and this. So that normal force has to be bigger than the weight. And then we want this diagram to screen to the right, so we really want this to be bigger than that. And that was page 1. Is that pretty much the way it went? Okay. Then you went to page 2. And page 2 is where 90% of the learning in that tutorial was located. You were told that the rope, the heavy rope, was magically, with the flip of a wand, magically transformed into a light string. But the hand is pushing now in such a way that the motion remains the same. Now folks, F net equals ma. A net force causes a mass to accelerate. With these dynamic problems, when we say motion, what we mean is acceleration. If the acceleration was 3 meters per second before, it's 3 meters per second now. But the hand's not pushing as much mass as it was before. The heavy rope's been replaced with a light string. So what does that tell me about the push by the hand? Is it the same as it was before? No, it's got to be less. It's got to be smaller. Now, we're going to play a game. These are the free body diagrams for the A, B, and the rope. And I want you to figure out how many of these forces will change when we go from the heavy rope to the light string. Okay? And here's how we're going to count them. I know that this changes. Okay? The heavy rope is changed for a light string, so this weight force gets smaller. That's 1. We count that as 1. But if I have a force that is broken up into components, if this one changes and this one changes, we'll count that as 2 separate changes. Okay? That's the way we'll count. Now what I want you to do with your neighbor is figure out how many changes you can find, and then use your clicker to let me know. How many changes can you find? Okay, it stopped boiling. Whoa! Oh, doggy. We're all over the map. Maybe it's a good thing that we're having this little talk. Okay, let's do it together. Let's start over here. This force here, does it change? No, just diet or exercise. Trust me on this, people. Diet or exercise. What about that component there? Yes, that's 1. Okay. What about that one there? Yes. That's 2. Okay. If this gets smaller, then that one has to get smaller. Now, folks, unless you get engaged to get married this week, the next question is the second most important question you'll be asked this week. The second most important. Does that component there change, yes or no, talk to your neighbor? Does it change, yes or no, talk to your neighbor?
Conflicting signals there.
Okay. Is the answer yes, no, or heck no? Heck no. Thank you very much. Heck no. And this is your reasoning. The mass of block A is not changing. It's the same block A. We're told that the motion stays the same, meaning the acceleration stays the same. If those two are both staying the same, then the net force has to remain the same on A. No other option. Now the net force is the extra force. When I add up all the forces, what doesn't cancel? Well, this cancels these two. That's what's left over. That's the net. It cannot change. Okay? Does that make sense? Now, so we've only got 2. We've got this one and this one, 2. So let's go over here. We said that one changes, that's 3. Does this one change? Yeah, if this one changes, that one changes by third law, so we're up to 4. What about that one? No. If this one doesn't change by third law, that one doesn't change. Okay? Now, what about that one? Yes. So that's 5. Now, folks, again, unless you get engaged this week, the next question I ask will be the most important question you will be asked this week. That one right there, does it change? Yes or no? Talk to your neighbor. Yes or no? Talk to your neighbor. Okay. I hope the answer that you gave your neighbor was yes. It changes. It has to change. And you use Newton's second law as your reasoning. When the mass of the heavy rope changes to a very small mass of a string, but we require everything to have the same acceleration it had before, did I draw that the same? Yeah. Okay. Because I'm multiplying that acceleration by a smaller mass, I'm going to have a smaller net force on the string than I had on the rope. Now the net is the extra, how much more force I've got to the right than to the left. This one can't change. So that means if the net's going to get smaller, this one has to get more like this one. It has to decrease and become more like this one. So let's count up again. We've got 1, 2, 3, 4, 5, 6. We're up to 6. This one? Yes. If this one changes, that's 7. This one? Yes. If this one changes, that one changes. We're up to 8. This one? Yes. If this gets smaller, this gets smaller. We're up to 9. And then, we already said the hand's going to be pushing less than it was with the heavy rope. So that's 10. The correct answer is 10. And if we go back and look at your... Oh, 13 of you got that right. Okay, we're ready. We are ready. Okay. Now, people, behold the power of PowerPoint. Pow! Want to see those changes again? You'll see them until you're dizzy. Now, right at the bottom of that second page, we wave that magic wand again and we change the light string into a massless string. Okay, and if you want to go through thread and then to the massless string, fine. But once we get to the massless string, this weight force has to be 0. And that means we don't need any sag. We don't need any of these vertical components. But there's something else that happens that's very, very strange when we get to the massless string. And that is when we look at the Newton's second law, F net equals ma. We've used this equation a whole lot of times when acceleration was 0. When you're building a building and it has no acceleration, all the forces have to add up to 0. You don't care how massive that building is. You don't care how big the mass is. You're multiplying by 0, the net force is going to be 0. Well, in this case, it's not the acceleration that goes to 0, but the mass of that string that goes to 0. And at that point, I don't care whether A is 3, or 6, or 6 million. I'm multiplying by 0, so the forces have to be balanced. And in that case, the free body diagram goes to this. And this force is exactly equal and opposite to that force. Okay? Now here's the thing. In every single introductory textbook for this class that's on the market, they always assume in every problem a massless string. And they talk about the tension in the string. Why is there only one tension in the string? Why isn't there a different tension at one end of the string than at the other end? And that's what we discovered in this tutorial. There is a very different tension at both ends of the string, unless it's a massless string. Now, folks, up until now, I have told you, I have asked you to always draw free body diagrams of everything in the problem. That was wrong. You know, I knew it was wrong when I told you. But I'm going to fix it now. When you have a dynamics problem, a force problem, I want you to draw a free body diagram of everything in the problem that has mass. Never draw a free body diagram for a massless string. Why? 2 reasons. First off, it's boring. It's just always the same. It's equal forces in both directions. But more importantly, it's confusing. This diagram screams to the right like it's supposed to. This diagram screams to the right like it's supposed to. This diagram will never scream, regardless of the acceleration. And hence, it's just going to confuse you. So never draw free body diagrams for a massless string. Okay? Now, some of you, I find, have an easier time of understanding this if we put numbers in there. So let's put some numbers in here. Let's say that the net force on A is 5 newtons. The heavy rope has a net force of what? Tell your neighbor, what's the net force on that heavy rope? I got 8 newtons and I got 5 newtons. Is the net force 13 newtons? No or heck no? Heck no. I've got 8 newtons to the right. I've got 5 newtons to the left. That's a net of 3 to the right. That immediately tells me that the rope has less mass than A. Because they've got the same acceleration, but that one's got a smaller net force. Now the net force on B is 12 to the right, 8 to the left. That's a net of 4 to the right. That means B, in my example here, has a bigger mass than the rope and a smaller mass than A. Does that make sense? Now, when we go from that heavy rope to the light string, I still have to have a net force of 5 on A. Its mass didn't change, its acceleration didn't change, I got to have the same net force. Likewise, I have to have the same net force on B. Its mass didn't change, its acceleration didn't change. Before I had 12 to the right, 8 to the left, that's a net of 4 to the right. Now I've got 10 to the right, 6 to the left, that's still a net of 4 to the right. It's the connector that changes the net force, okay? With the rope, I needed 3 newtons to make that heavy rope accelerate to the right. I needed 3 more to the right than I had to the left. With a light string, I don't need 3 newtons. 1 will do it. And so this force gets closer to that force. And the smaller the mass, the closer this will get to that. Until I reach the massless string, and then they have to be the same. Now don't confuse the net force with the force. The net force on a string has to be 0 if it's massless. But I can have a force at one end that's 1,000,000 newtons as long as I have 1,000,000 newtons pulling at the other end. Okay, is that clear? Okay. Now, in the defense of those big intro books that cost $240 that always assume a massless string, in most situations, the mass of what you're pulling, like a car, is going to be large compared to the mass of the thing you're pulling it with, the rope. And so we can neglect, in many cases, the mass of the string or rope that we're using. Besides, they did not want to get into all the mess that has to do with this sagging. That was just one bridge too far, they thought. Now, I'm here to tell you that back 25 years ago when these tutorials were written, I was sharing an office with Peter Schaefer. And we had a big discussion, and in that discussion, we said, you know what? They're having a hard time with that tutorial. What if we take the rope and we connect it here so that it just slides across the floor? We'd still get the same idea across, but there wouldn't be all this mess in the free body diagrams. And I remember it was Peter Schaefer, Lillian McDermott, myself, and Mark Summers in that room. And we paused, and then Lillian said, no. That mess is good for them. That mess is going to make them better people. And you're better people now. I can tell. I can see it. You're better people. Okay? So we put it up here and let it have the mess. Okay. You took this pretest last week, and you had 2 books, A and B had a greater mass than A. And you had this question. The force exerted by string 1 on book A is less than, equal to, or greater than the force exerted by string 2 on book B. Tell me again how you answered that. How did you vote? Okay, last call. Oh, again, we're all over the map. Now, this particular pretest I have done a lot of research on. I used to collect them from every class until I got a great big mountain of these pretests. And then I poured through them one at a time, trying to find out why people were getting this wrong. What mistake in their reasoning were they making? And what I found was that there were many, many different ways to get this wrong. And it was discouraging to me. I was thinking, man, everyone gets it wrong for a different reason. And then I started to see a pattern. I found that if a pretest had a free body diagram on it, that person was almost always going to get it right. If the page did not have a free body diagram on it, that person was going to get it wrong for any one of many, many reasons. It's hard to even keep track of all the reasons, but you're going to get it wrong. So let's draw a free body diagram. Well, a free body diagram of what? Well, normally I'd draw a free body diagram of everything with mass. But in this case, I'm trying to compare the tension in string 1 to the tension in string 2. So it makes sense to draw a free body diagram that has both of those forces in it. Which book is acted on by both strings? A. So if I draw a free body diagram for book A, I have a weight force down, earth on A. I then ask, are there any magnets? No. So what touches A? Well, string 2 pulls back. I'm also told that string 1 pulls forward. And what else? Whoa, the floor. The floor touches and it pushes. Whenever one thing pushes on another, there will always be a normal force. There may also be a friction force, and in this case we're told there is a friction force. It's kinetic friction by the floor on A. And that's my free body diagram. Well, that's not helpful. It's not helpful until I use the fact that the books, both A and B, are speeding up to the right. So they have an acceleration to the right. That means this diagram that I just drew has to scream to the right. That means this tension force by 1 on A has to be bigger than the tension force by 2 on A, plus the friction force of the floor on A. It's got to be bigger than these two combined. And so that tells me that the tension by 1 on A is greater than the tension by 2 on A. Well, folks, that's not what was asked. What was asked is, how do I compare the tension by 1 on A to the tension by 2 on B? Well, if I want to do that, I have to know how these two forces compare, 2 on A and 2 on B. How do those compare?
Equal.
They have to be equal. By what law? It involves both the second and the third law, but we're going to call it the law of massless strings. In this class, we're going to have a law of massless strings. And that law is just that if it's a massless string, I got to have the same pole at both ends of the string. Okay? Now, if this is bigger than that, and that is equal to that, then this has to be greater than that. So the tension in string 1 on book A is greater than the tension by string 2 on book B. So the correct answer is C. 35 of us got that. Okay. I hope that everything is just coming together and it's starting to feel really good. I also hope that Christmas will be here soon. Okay. I go down to Home Depot and I get 3 completely identical cinder blocks. And I hang them using massless strings as shown. And the question is, how do the tensions in the string compare? The tension in the left string is less than, equal to, or greater than the tension in the right string. So tell me with your clicker what you believe. Okay, that's all of us. The answer is equal to, okay? And these problems are best answered with a free body diagram. If I draw a free body diagram, and I assume, I'm making this number up, that the weight of this cinder block is 50 newtons. There's no magnets in this problem. The only thing touching the cinder block is the string, and it pulls with a tension force. Now that block is just sitting there, which means it has 0 acceleration, which means its diagram has to scream balance. And my question is, which cinder block did I just draw the free body diagram for? All 3. And so the 2 strings have to have exactly the same tension in them. Now, some of you are saying, but wait, Greg, this one's got 2 blocks pulling on it, and this one only has 1 block pulling on it. Well, the answer lies in how we define tension. If you take a rope, say that rope is supporting some mass. If I take that rope and I break it and I put in a spring scale, the tension is defined as the reading on that scale, or how hard each part of the rope is pulling on its neighbors. If you think instead of a rope, a chain, it's how hard each link of the chain is pulling on its neighbors. Now, suppose I had a spring scale, and there's the hook, and I hung on that spring scale a fish that was caught. I didn't catch it, I don't fish. Okay, but someone caught it. Okay? And let's say that the reading on that scale is 3 pounds. Okay? Now I'm holding it, I'm holding the scale. In order to hold that scale up, I got to pull up on the scale with 3 pounds while the fish is pulling down with 3 pounds. But the reading on the scale is just how hard we pull on this hook, not how hard you're pulling up on the handle. And so the reading on the scale would be 3 pounds. Now, if I go here, and I look at this string here, that string is not moving right there. Now, whether that string is not moving because I've got another block pulling down, or whether I've tied it to the wall and the wall is pulling on it, it doesn't matter. I get the same result either way. And so the tension in both of those strings is exactly the same. Check to see if your neighbor believes that. Okay? Okay, last day I gave you an exam preparation sheet. That exam preparation sheet has this old exam problem on the back. Would you get that out, please? And those of you that didn't bring yours, raise your hand. These are bad people. Bad people, okay? 3 bad people in this row. Oh, they're proud of their bad. Yes, they are. They're responsible for their bad. Okay. And we're gonna end up in 10, you know that, right? Okay. Who else needs one? Those extras? Does anyone else need one? Coming down, sir. Okay. In this problem, we have a block B pulling a block A up a frictionless incline. The angle of that incline, of course, is 37 degrees. Why wouldn't it be? And we're told that block A is moving up the incline at constant velocity. Now on exam questions, when you see those words constant velocity, that should set off bell. Ding, 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 ding. Zero acceleration. Balance. Equilibrium. Now the first thing you're asked to do is draw free body diagrams for A and B. And I always encourage you to draw the free body diagram of the simplest object first. The object that's touching the fewest other things, which in this case would be B. So draw your free body diagrams. Okay, we're only going to get halfway through this today. We'll finish this up on Wednesday. But because we have 2.5 minutes left, let's do the free body diagrams together. I start with B. I put the weight force on there, Earth on B. I then ask are there any magnets? No. What touches B? The string, and it pulls. Now I know that if A is going up the ramp at a constant velocity, B is descending at a constant velocity, so this has acceleration 0, and it should scream balance. Now I go to A. The first force I put on that diagram is the weight force, Earth on A. I'm told in this problem that's a 50 Newton force. I then ask are there any magnets? No. What touches A? Well, the string pulls up the ramp with a tension force, and the ramp pushes with a normal force, but not a friction force. And so those are my free body diagrams. Now, whenever I have a ramp problem or a hill problem, I rotate my coordinate system so that it lines up with the ramp. And then this normal force will be in the y direction. The tension force will be in the x direction. It's always the weight force that we need to break up into components. And we always do it the right way. We look in the direction of the normal force, we go the other way until we can make a 90-degree turn, there's a 90-degree turn, and get to the end of the vector. This is going to be the x part of the weight, this will be the y part of the weight, and this angle will always be the angle of the hill. Now, because that's 37 degrees, this is going to be a 3, 4, 5 triangle. Once I break it up into parts, I throw away the original. Since this has 0 acceleration, I have to have balance in the x direction. In the x direction, I've got one force up the ramp, one force down the ramp, so this must be 30 newtons. In the y direction, I've got one force in the positive y direction, one in the negative y direction. This has to be 40 newtons. Now, if this string is pulling 30 newtons on A, it's a massless string, so it's pulling 30 newtons on B by the law of massless strings. If this diagram has to scream balance, the weight force is 30 newtons, which means the mass of B is 3 kilograms. We'll go over that in more detail and a little slower on Wednesday.